Stripping down science. The Naked Scientists.
This week, the Naked Scientists are travelling to the University of Oslo in Norway. Awaiting you in the programme, dinosaur dissections, ultra-efficient solar cells, new ways to combat cancer, mass extinctions, and...
You have sperm from, for instance, nematodes, these small worms you don't want inside you, which are maybe a couple of micrometers big, to Drosophila sperm, reaching almost 6 centimeters.
6 centimetres, yeah. But they're flies. They're tiny flies.
Yeah, that's correct. The sperm length is actually 10 times the length of the individual.
Thank goodness we're not flies. Hello, I'm Chris Smith, and our first stop is the basement of the Oslo Natural History Museum, where Espen Knudsen is reassembling the remains of something you really wouldn't want to swim with.
If you think yourself a turtle maybe without the shell, and you add a long neck to that, and sometimes a small head and sometimes a large head, depending on what sort of plesiosaur we're talking about, then you basically have the plesiosaur body plan sort of laid out.
Were they vicious?
Some were. Most of the ones we have here from our locality at least are small-headed with very... I mean, the head is probably about 30 centimeters long and the teeth are very slender, up to maybe 2 centimeters long and very thin, perhaps half a centimeter or so in thickness, and probably ate mostly squids and small fish. And then you have the large-headed pliosaurs, which is another group of plesiosaurs that have heads up to maybe 2.5, 3 meters.
Meters?
Yeah.
and teeth, how big?
Teeth like cucumbers, basically, yeah.
And probably quite a bit sharper too. So they're eating things they would have found in the sea?
Yeah, they would... The pliosaurs obviously would probably eat anything they would come across, plesiosaurs or ichthyosaurs, which are the other group of marine reptiles we find there, and also larger fish.
If they're living in the ocean, it would have been pretty cold here, wouldn't it? Yeah,
the temperature in the ocean 150 million years ago in Svalbard is estimated to have been about 10 degrees based on isotope analysis, which is obviously cold for a modern-day reptile, at least. If you put a snake in 10-degree water, it's not going to do much. So obviously these reptiles would have had some way of keeping themselves warm, whether they were endothermic or just stayed warm due to their large sizes. It's still unknown, but maybe in the future we'll know some more about that.
Big fish like salmon sharks are effectively warm-blooded because the core of the animal is so far from the outer part of the animal where the water is cold that just metabolism alone means that they're running at near human body temperature inside, and the stuff closer to the surface less so. So do you think these plesiosaurs were probably similar?
Yeah, possibly, at least the large pliosaurs. It's a bit different with the smaller plesiosaurs because they have a fairly larger surface area compared to body volume, and they might even have migrated south parts of the year. Maybe the sea temperature was a bit warmer in the summer. And obviously there's comparable faunas in England at the same time, and they might have migrated back and forth through our locality and the English localities annually, perhaps.
When were they swimming around?
All of our animals are from the late Jurassic, which is right on the border to the Cretaceous. So we're talking about 150, 140 million years ago.
Would they have evolved originally in the ocean and stayed there, or could they have come out of the land and gone back into the water? Do we know where they came from?
We don't know too much about the origin of plesiosaurs, other than that they originated from land-living tetrapods. So there was some sort of reptile that once in time in the early to middle Triassic started wandering into the water and adapted to an aquatic lifestyle there. And we do have middle to late Triassic Sauropterygian, which is this group, fossils from other places in the world, which are sort of a precursor group to these plesiosaurians.
It's quite interesting that the invasion of the land happens from water onto land, and then the animals go back into the water, obviously because there's some kind of niche there. And now here we are, 100 million plus years later, finding them. So how do you go and get these specimens?
Well, how this all started is basically we go walk around on the Svalbard, and it's quite barren up there. It's basically an Arctic desert, so there's not much vegetation. So we can walk around and look at the surface for bones that have weathered out from the surface and roll down the hill. And then we follow these little bone pieces uphill, and we can find the source sometimes, and other times we don't. And then if we do find the source of the pieces, then we can start brushing slowly in, and maybe there's more coming out, and maybe there's not. And if there is, then we can start excavating whatever's in there. And based on what we can see from the preliminary excavations, we decide whether or not it's worth starting to excavate, because it's quite an ordeal to remove tons and tons of overburden. Every year we remove by hand 100 tons or so of shale. So we want to be a bit picky about what we're actually taking out. And
when you spot one, how do you get it out?
Yeah, once we've finally decided which one to take out, we remove the overburden, brush clean the surface of the bone, then we add wet toilet paper and some wet plaster and a piece of burlap dipped in that plaster, and then we cover the whole thing with plaster and iron and so on until we have a lid. Then we dig down around the lid, around the specimen, cover the sides with more plaster, and eventually we have sort of a mushroom of plaster, shale and bone that we flip to the over to the other side, and then cover the other side with the same wet toilet paper and plaster again, and we cocoon the whole thing in that and transport it back to the museum.
So that's the summer job, and then winter time comes, and you're here in the lab now picking apart that mushroom or that cocoon, that plaster cocoon, to get the find out. So how do you then process it? Because what have we got here? Because this looks like a bed of plaster. Is this one that you've basically got going here? Yeah,
so this is plesiosaur that we've already prepared from one side. So what we do when we come into the lab, we first let it dry for a couple of months, because we can't glue it when the specimen is wet. And then we have a little saw that we cut the cocoon open and start picking away with little tweezers and little brushes all the loose shale, and simultaneously glue and stabilize the bones. And then once one surface is done, we can toilet paper and plaster jacket that side, and then we flip the whole thing and take the lid off the other side and do the same thing there. And eventually we get this nicely looking specimen here with no shale and basically stabilized bones. And then Miley-Lis that's sitting here, she's a preparator here. She scrapes away excess shale and gypsum crystals that sometimes grow on these bones and stabilize the specimens further.
Can you give us a guided tour of this one that we're looking at? So there is in front of me the size of a large dining table with I can see some of the obvious bones. There are vertebrae and things all encased in here. But can you talk us through this fossil and just explain what the various bits are?
Yeah, so this is parts of a plesiosaur that we excavated 2 years ago. And what we have here is we have the whole vertebral column from the head, which isn't here now, where we have that in separate jackets, and through to the body and the shoulder, and then we have parts of the body, and just before the hip, the rest of the skeleton has weathered out, and we have...
Are there ribs there?
Yeah, all these, the ribs, body ribs, and then you have the neural arches, which goes on top of the vertebra there, and then all these flat bones, the 4 flat bones are here, are from the shoulder girdle, which is on plesiosaurs. It's basically just a flat plate on the front of the chest, and to that connects the front limbs. So we have the upper arm bones here, and the lower arm bones are reduced to these very short triangular looking things, and then all the fingers are coming out nicely here, forming a flipper.
Is that effectively the wrist there? Are they sort of the equivalent of carpal bones?
Yeah, all of these little round bits are the wrist, and this one and this one, these 2 triangular bones, which are the size of, I don't know, one is the size of a coin, and the other one's twice as that size. They're the lower arm bones, so the radius and ulna that we have.
And then these little ones, are they the equivalent of phalanges in me, the finger digits?
Yeah, that's all phalanges. So what we have in plesiosaurs is something called hyperphalangy, which means that they increase the number of phalanges within each digit, which is something they do to form this paddle shape of the limb.
So what's special about the dinosaurs that you're getting at, or what's special about the Svalbard specimens compared with ones that we'd find elsewhere in the world?
Faunal composition-wise, It's basically the same. We have the large-headed pliosaurs, we have the long-necked plesiosaurs and the ichthyosaurs. But all of these, when you look and go into detail and look at all the details of the limbs and the vertebral column and the shoulder and so on, are slightly different from what we see from other places like the Kimmeridge and Oxford clay in England, for instance. And all actually constitute new species. So we have 5 new species of plesiosaurs and 4 new species of ichthyosaurs from this place, and we still keep digging out more every year. We have 30...
Are there lots of them?
Oh yeah, we have 31 specimens so far, and probably another 60 out in the field that we have mapped already, and we find another 10 or so every year as well.
So what do you think will be the ultimate outcome for this one? Because I can see the bones have all been glued together. Will you actually be able to assemble this?
Well, this one is actually special that it's articulated. All the bones are laying in the position where that they were when the animal was alive. The problem is that the animal has fallen onto its back when it's hit the sea bottom, so the rib cage and everything has collapsed on top of the vertebral column. But all of these bones go nicely together, so what we're going to do eventually, when we get the room as well in the museum, because it's a big animal, probably 4 or 5 meters long, we want to reassemble all the bits and lay it out nicely so people can come and view it.
Espen Knudsen. Something we are notoriously bad at is making efficient use of the energy in sunlight. And that's because the materials that we currently use can only make electricity from red-coloured light, so the extra energy in the other colours is wasted. But Per Anders Hansen might have a solution.
Sunlight consists of small energy particles called photons. And these can have a lot of energy, like ultraviolet light or blue light, or they can have medium energy, like red light or visible light, or they can have very little energy, like infrared or heat radiation. And when these photons hit the solar cell, what they do is that they knock loose one electron, and this electron can then travel around in our circuit and give us power. And to do this, the photon needs a minimum amount of energy. But if they have more than this, they still only knock loose one electron. And this is why solar cells are not more efficient. They could be like 2 or 3 times more efficient.
So if we had a way of taking some of those photons that are very high energy and converting them into more photons at a lower energy, we could get more electrons out, and therefore the overall efficiency of the cells would be much higher.
Exactly. If you take these high energy UV photons and simply like cut them in 2, cut the energy in 2, so we have 2 particles of half the energy, then you would get twice the amount of power out of those photons.
Can we do that? Can you convert light of one wavelength, like UV, into a longer wavelength like that, like you're saying? Is that possible?
Yeah, it's possible, and it's actually quite easy. It's easy to turn one photon, one ultraviolet photon, into one visible or one red photon. That's actually quite easy. That's what's going on in fluorescent tube lightings, actually. So that we sort of know how to do. The tricky part comes when you want to cut it in 2, so that you get actually twice the amount of light or photons out from the ultraviolet light. That's where the trouble is. We can do that for very high energy photons. That has been done very efficiently. The trick is to do it for photons that actually exist in the sunlight. That no one has done yet.
So we know how to do this for high energy photons like ultraviolet, but because there's not much ultraviolet reaching us here at the ground, you're saying that although the materials exist to do it, we haven't got really the light that can make use of that. So we need a new material that will work with the photons we do have and cut them in this way.
Yeah. We know how to convert very high energy ultraviolet light that exists like in space outside our atmosphere, but the ultraviolet light that comes down to Earth, like we get sunburnt off, it doesn't have enough energy to work with those kind of materials.
How are you grappling with it? What are you doing to try and overcome that?
Well, I use a very peculiar synthesis method called atomic layer deposition. It gives me a very high control of which atoms sit next to each other. You usually have 2 components in this kind of material, something that absorbs the light you want and something that emits the light you want. And you need these to be sort of in every other position. So you have something that absorbs, and around it, it has to sit these emitters. And around the emitters, it has to sit absorbers. So if they are mixed up randomly so that you have one bunch of emitters over there and one bunch of absorbers over there, it's not going to work. But if you can really control what's next to each other, you have a lot more control of what's going on and the physics that's going on in the material.
So would that array work because the absorber soaks up the energy and passes it to the emitter next door, which then spits out the photons of the wavelength you do want, and they're then carried off and absorbed into the semiconductor material to actually make the current?
Yeah, that's exactly how it will work.
So what materials can we use? Are you basically trying different combinations of anything to see if you can get the right sorts of absorption and emission, or do you already have some candidates that you know are the right sorts of chemicals to use?
Yes to both. We know what we need. We just need something that absorbs ultraviolet light and blue light, and many things do that. So, for example, sun cream absorbs ultraviolet light. Sun cream consists of titanium oxide, for example. Okay, titanium oxide, that could maybe be a good candidate. Then you just need to find something that emits light very well. So then I have thought of, okay, what emits red? A TV emits red. In a TV, what is it that makes TV go red? It's europium. So combine those two and that works. So, of course, that is not my big secret. My big secret is more fancy than that. But that is kind of the quest you're going through. Just what can absorb it and what can emit what I want, and then just combine it. And then you need to combine it in a very particular way so that everything sits at the right place.
So those atoms are deposited in just the right configuration.
Yes.
If you can get this to work, what sort of step change in efficiency could we achieve with a photovoltaic? What will it go from to?
Well, a normal silicon solar cell that you can buy on the market today, it's between 16 and 20% efficient usually, maybe a bit more sometimes. But for red light, or light between red and 900 nanometers or something like that, it's actually much more efficient. It's more 60, 70, 80% efficient. So if you actually can take all that other energy, convert it to red light, then it's actually no problem to just take the normal solar cell that you have at your cabin, and you suddenly get 50% efficiency out of it.
Which is a dramatic improvement. I think the figure is something like the amount of sunlight that falls on the Earth in one day is equivalent to the amount of energy that the entire world consumes in a year. So if we can get cells up to those sorts of efficiencies, we actually could do quite a lot to offset what we're concerned about, sort of climate change and all that kind of thing from the energy industry.
Yeah, we have plenty of sunlight. If we can just convert it efficiently and, of course, cheaply, then actually we don't really need anything else.
So how far away do you think you are from realising the technology you're working on? How long before we see these novel coatings going onto photovoltaics so that you can harness the extra energy we're currently just chucking away?
There are some testing going on now around the world of doing this one ultraviolet into one red or something like that photons going on today. But this 1 to 2 photon cutting, that has not been done yet, but I hope that we can maybe see that around the world in maybe 5 years, 10 years, I hope.
So I need to come back in 5 or 10 years and see if you're right.
Yeah, come back then and see how I'm doing.
I'll do that. Per Anders Hansen. Lemmings now, and although these animals don't really throw themselves off precipices, in recent years their population cycles have nosedived. The reason, discovered by ecologist Niels Christian Stenseth, is one that British train companies would be proud of. It's down to climate change causing, you've guessed it, the wrong sort of snow.
A lemming is a small rodent, and the Norwegian lemming is a very charismatic one, yellow and black. It used to be that every 3 to 4 years there were massive numbers of lemmings in the mountains. Then the next year it was gone. That is what we refer to as the lemming cycle. And the lemming cycle occurs for lemmings as well as for many other small rodent species. And the lemming cycle was a characteristic feature. There's written many stories about this, the translation of the Bible to the Nordic languages, the swarms of grasshopper in the Middle East. There was a footnote by the translator saying that this is like lemming cycles. So it's a well-known phenomenon. Since the mid-90s, there has been no regular lemming cycles.
Well, they just stopped, just vanished.
It vanished, and that is well-known.
But the lemmings are still there, they just
lemmings
haven't...
are still there, but the massive occurrence at a regular time periods disappeared. So that has been an interesting thing to try to find out why. And we did a work doing time series analysis, statistical time series analysis, where we looked at the dynamic structure of the lemming population and how that was affected by climate, temperature and precipitation and the like. What we found was that the kind of snow that was falling was critical determinant of whether it was going to be a regular cyclic phenomenon or not. It used to be that when snow came in this part of the world, it was cold, so it came as dry and soft, so that a small space between the ground and the snow could build up. And within that space, lemmings could survive very well, and they reproduced and built up a population that was high in the spring and could then continue to be high if it didn't crash during the summer.
But why would their population have this 4-year cycle? Because the snow's going to come every year, so why does the population grow and then suddenly plummet?
When they crash to very low densities, and they crash most likely because of the predator population building up. So they crash to very low levels, and it takes time for them to build up. And to build up at very high densities, they need a period that they are free from heavy predation, and that's what they get during the snow, during the winter period. And it takes 3 to 4 years to build up such a population. But in the mid-90s, all this was gone. And what we found in this paper published in Nature was that the snow had changed also from being soft and dry to wet. Hence, the lemmings could not build up. 1 year ago, I predicted that there would be a lemming peak all over Norway, as a matter of fact, all over Scandinavia, because the previous year had been very cold, very good snow condition, and we were then in the middle of a good winter, and true enough, it was a lemming peak last year, all over Norway.
So are you seeing a return to nice cold winters again, or is the snow still unreliable and soft and wet?
Well, I'm not a climatologist. It so happened, I think, that it was 2 good winters for lemmings. Climatologists tells us that won't be a regular phenomenon as it used to be. So I think the lemming cycle has not come back. I think the lemming cycle has gone, but you will occasionally have high years with lots of lemmings, but it won't be regular.
What's that done to the predators? And from an ecological point of view, what are the onward consequences? Is this just a sort of mathematical phenomenon that if the conditions come right again, it will re-establish? Or are there going to be onward impacts which are irreversible?
I think the lemming cycle will come back if the climate changes. But it might take quite a bit of time for the whole ecosystem to recover. Because when the lemmings are gone, that affects ptarmigan. Because when predators have no lemmings to eat, they will go to other species, including ptarmigan. It also affects the interaction between the Arctic fox and the red fox. The red fox being competitively superior to the Arctic fox, unless there are lots of lemmings, then the Arctic fox does well. So it will change the whole ecosystem. So maybe the Arctic fox will go extinct on the mainland and only survive on the Svalbard, Spitsbergen, in the Norwegian territories.
Niels Christian Stenseth.
Distilling the best science. The Naked Scientists.
You're listening to a special Oslo edition of The Naked Scientists this week with me, Chris Smith. And now to cancer and how to persuade the immune system to attack it. Alexander Corte.
We know that the immune system protects us against cancer. But it's still very little known about how the immune system protects against cancer, and this is what we are trying to find out. We are using an experimental system in the mouse. The type of cancer we're studying is bone marrow cancer, it's called multiple myeloma, and also lymphoma. We're interested in immune cells called T helper cells. So we are interested in how T helper cells fight cancer.
So can you talk me through the experiments you've been doing in these mice to work out how the immune system usually protects them and what goes wrong when a cancer occurs?
What we think is going on when people develop cancer is not that there is anything wrong with the immune system. What we think is going on is that the cancer cells somehow manage to fool the immune system, to evade the immune response, presumably by producing molecules that will suppress the immune system.
When a cell becomes cancerous, how does the immune system pick that up normally and remove that cell to stop a cancer occurring?
There are two major ways. One way is by recognizing stressed cells. So any stressed cell in your body will show it on the cell surface. There are some stress markers. And that will be recognized by the immune system, and the immune system will simply kill the stressed cells. The other ways, which is even more refined, is that the immune system is able to recognize mutations in cells, mutations that are required for normal cells to become a cancer cell. There's a certain number of mutations in the DNA that are required. And the immune system is able to recognize not directly the mutations, but the effect on proteins.
And any cells displaying that sort of danger signal are just going to get deleted straight away.
Exactly.
But obviously not all the time, because otherwise no one would get cancer.
So most of the times, and that's why most of us do not have any cancer. It's also probably the reason why it takes so many years to develop cancer. Usually people develop cancer after the age of 50, so we are extremely well protected against cancer. But sometimes the cancer cells manage to evade the immune response.
And how do they do that?
It is not well known yet, but one major way to do that is to use the communication system that the immune system uses. So immune cells communicate with each other. And cancer cells are known to produce some signal molecules that the immune system uses normally to suppress itself. At the end of a normal immune response, the immune system shuts it off. And this is probably what the cancer cells do. They tell the immune system to shut off.
So by chance, the cancer evolves the ability to produce some of the chemicals that would normally damp down the immune response, thereby effectively putting it under the immune radar. It's just looking like healthy, normal tissue to the immune system, or it's basically suppressing the immune system where the cancer is, stopping it being destroyed.
That's absolutely correct. But I should stress that there are some very good indications that the immune system never gives up. So even in a cancer patient with established cancer, the immune system still fights back, and there is a battle going on in the cancer patient. And this is very important because it means that it should be possible to stimulate, to help the immune system to tip the balance towards cure of the cancer patient. And this is something we really hope for the future.
Well, people have been working on the field of immunotherapy, haven't they, where the idea is you would take some of the tumour out of the patient, take immune cells from the patient in the dish, and use growth factors to try and drive the immune cells very hard to overcome whatever that inhibition is coming out of the tumour. And sometimes you get immune cells that will attack the tumour, but often not, because there have been a few case reports written up, haven't there, of people who have had complete remission of cancers that way, but all too often it doesn't work.
Yeah, so this is correct. What you're mentioning is called adoptive T-cell transfer, so culturing T lymphocytes in vitro and then giving them back to the patient. And this has shown some very promising effects. One key issue there, which is also valid for the development of cancer vaccines, one main issue there is to know what type of immune response to trigger. Many different types of immune responses are used by the body against various types of infections or cancer. And it is still not very clearly known what is the right type of immune response that is the best to fight cancer. And this is what we're working on.
What have you found so far?
We have found that in a certain mouse model that the optimal immune response to fight cancer is an inflammatory immune response driven by a type of T cells called Th1 cells.
And if you could induce that in people who have a cancer where the immune system is not combating it, would that push the cancer into remission then?
This is our prediction. This would be the two arms of the immune system to stimulate. In one way, to stimulate an inflammatory environment, especially in the tumor, which would be very important to recruit immune cells, in particular T cells. And the other important aspect is to stimulate Th1 cells, which recognize very specifically the cancer cells and which tell other cells to kill the cancer cells.
What about risks, though? Because one worries that if you get the immune system attacking what is self-tissue, it's your own body, there's a concern that the immune response might spill over and become mistargeted away from the tumour and at healthy tissue, and you then end up with an autoimmune disease.
That's correct. So one should be always very careful when triggering the immune system because, as you said, the immune system is very potent. It may trigger autoimmune diseases. It may also kill you if the immune response is too strong. However, cancer is definitely very dangerous to people. Cancer is killing people. And on the other hand, current cancer therapies are also very tough to the patients, like chemotherapies and irradiation. So I think there's always a balance, but I can really see a future where immunotherapy will be perfectly developed and will help the patient with minimal side effects. But of course, when you treat a serious disease, it is very difficult not to have any damaging effect on the patient at all.
And the results you've got in the mice with the hematological tumours, will that transfer directly to other kinds of malignancy?
We cannot say that yet, but in my view, yes. And from the literature, not much has been done on at that level of details, but it looks very much like this is a general way of how the immune system fights cancer, so this Th1-driven inflammatory response. That's my expectation, that this will translate to other types of cancer and also to human.
Alexander Corte. Another very effective cancer treatment is radiotherapy, but this can have side effects when healthy tissue is also harmed, and that's because although most cells can be killed by very small amounts of radiation, the dose has to be high enough to prevent cancer cells becoming resistant to the treatment. Now, though, Nina Edin and Erik Pettersson have discovered how cancer cells become resistant and how to turn this off.
About 80% of all cell lines that have been investigated, and we believe most normal tissue, have a property which make them very responsive to radiation doses at about 0.3 gray, which is about a tenth of the normal dose you give in radiation therapy. So if you can exploit this feature, then you can give much smaller doses altogether and spare the patient for a lot of radiation to the normal tissue.
Okay, do we understand the mechanism, and are we in a position to put cells into that hypersensitive state so that we can use very low doses of radiation to destroy them without having to do lots of other damage to healthy tissue in the body?
The problem is that when you give a small dose, then you induce a resistance to the next little dose.
So you give the small dose, you will wipe out some cells, but there will be a small hardcore group left behind that you won't get rid of, and moreover, they will be resistant. Then the next time you come in with another small dose, they're just not going to be destroyed.
No.
So how can we get around that?
Well, what we really have discovered is that something is secreted into the medium that can be affected by low-dose irradiation, but not by high-dose irradiation.
So you're saying that cells have an ability to detect radiation at a low level using a receptive molecule, which then leads to the secretion of a factor, which then in turn renders the cells resistant thereafter.
Yes, that is what I say. And we have found the mechanism in the cells that keep this factor secretion going, and we've found a way to inhibiting this mechanism.
What are the chemical nuts and bolts that are doing this? What are the molecules that are doing it?
The molecule that induces the resistance is TGF-beta3, which is transforming growth factor 3. The mechanism depends on INAS, inducible nitric oxide synthesis, and if we inhibit the effect of this molecule, we can stop the whole process and reverse the cells to the original hypersensitive state.
So what locks that effect in the cell?
It has to do with how the TGF-beta3 works, because it is only active when it is not bound to a molecule called LAP. So this LAP inhibits the effect of the molecule, and it's sort of a system to control the activation of it. So what happens is that nitric oxide synthesis produces nitric oxide, and this nitric oxide takes away the LAP so that it cannot reassociate with the TGF-beta3. And then this remains active inside the cells and starts some other processes that makes it that all go around like a self-sustaining mechanism.
So putting that together, you have a small amount of radiation, and that triggers
the activity of this INOS, inducible nitric oxide synthase enzyme, which makes some nitric oxide, that removes the LAP molecule, which activates the TGF-beta molecule, and that then triggers a locked-in change in the biochemistry of the cell, rendering it resistant to more radiation. So if we block those actions, then the cells would remain potentially hypersensitive to these very low doses of radiation. So, Eric, how could you use this knowledge?
So far we have been talking about cancer here, but this could have some influence also above or in other areas. TGF-beta then seems to be able to turn off hypersensitivity. And for a person who have been, for example, experiencing irradiation, that could be very positive, because often that would be small doses, and if you could, for example, increase TGF-beta 3 in some way after a very small dose, that might actually influence on the response of this radiation. So this could have some influence. We don't know this yet, but this could have some influence also in other areas than just cancer research.
So if we had a way of addressing the signal to healthy tissue, we could protect healthy tissue, we could leave cancerous tissue vulnerable, and this means that anti-cancer therapies like radiotherapy could be made much more effective at much lower doses.
By targeted administration, for example, that could be a possibility. The important thing is that we have sorted out a mechanism which influences radiation responses at very low radiation doses.
And Nina, why do you think cells have this anyway? What's it there to do, this mechanism, normally? Why has evolution selected it?
That's a good question. I'm not sure. I think it does more things than we know yet. So I'm not sure that this only addresses hyperradiosensitivity. I think it's a kind of a stress response. But one thing I didn't say was that we have also tried to administer the TGF-beta 3 after irradiation, and it has effect also 4 hours after you've been given the radiation, so it works backwards, which also is interesting if you have accidents.
And what could be the consequence of deactivating that signalling in healthy tissue? If you block the ability to see TGF-beta like that, will the cells in any way suffer?
This is a very good question, because when cells respond by hyperradiosensitivity, it could be a normal response just to get rid of cells which have got some radiation damage, just to get rid of them. If the damage is not too bad, they can be easily restored by stem cells, from stem cells. But if the damage is going on for a long time, then they have the possibility to turn off the hyperradiosensitivity, do the repair, and maintain the tissue by taking care of the cells. So this could be a normal process which has some meaning in the restoration of tissues in general. And we have some indications that this protection, we should call it protection, of course, not only works against radiation but also against some toxic chemicals. So it's a more general stress factor than just radiation.
Eric Pettersen and Nina Edin. Mass extinctions now, and Henrik Svensson is trying to work out why they happen. The answer might lie beneath our feet.
Let me bring you back 10 years or 15 years when my colleague, Sverre Planky, discovered some amazing structures from seismic data offshore Norway, almost like big volcano structures. You can see them on seismic reflection data, extending perhaps 4 or 5 kilometers down into the seafloor. And he was really intrigued by this and wanted to understand what they were.
How big are they then in terms of cross-section? Because obviously that's very tall, but what about across?
Up to 10 kilometers across. So really big kind of crater structures. And to make a long story short, I started doing work in South Africa to look at fairly similar type of structures exposed on land to really get a better feeling for what this could be. What I found was really amazing. I found big structures, big craters filled with crushed rocks, but I didn't find any volcanic rocks. So my conclusion was that these structures were formed by gas release, explosive gas release from the Earth's crust, and that the gas release was triggered by the action of igneous rocks melt in the Earth's crust.
Why did they form where they formed then?
They formed because in the subsurface, 183 million years ago, that part of South Africa was intruded by melt. And the melt triggered gas formation, and that led to overpressure, and then blowout structures, almost like volcanic structures, releasing the gas to the atmosphere.
It's like an exhaust pipe for a volcano.
Yes, that's a fairly good description.
And what would be the effect of these things? What would come up through them, for how long, and what would be the local environment?
That's been a subject of research for many years, and we have different approaches to this. We do the fieldwork, we look at the minerals inside these pipe structures, and we also do theoretical modeling to understand what's coming out of these pipes. And in conclusion, the gas composition that's coming out is related to what type of rocks are heated in the subsurface. So if you heat sand with pore fluids, with water, you form water vapor. If you heat shales, which is rich in organic matter, you might form methane or CO2. But for the case of South Africa, the main gas component, we think, was methane. And then, of course, things start to get interesting, because methane is a greenhouse gas. And we're trying to quantify the volumes of gas release, and it's definitely within the range that it would have created global warming if it was erupted fast enough.
Gosh, so how long would these things have remained active, do you think?
That's a question which is extremely difficult to answer. We're doing the best we can with the best available methods, and we can say that everything happened within 500,000 years.
That's quite short, isn't it? What sort of volume of gas are we talking about?
Billions of tons of gas.
Gosh, so that's going to be quite a few degrees, potentially, of global temperature change, if all that sort of gets burped out in one convulsive release.
That's right. And if you look at what happened on Earth at the same time as these pipe structures formed, there was indeed a global warming episode in the early Jurassic. So we think that perhaps these two could be linked together. The main challenge today is, however, to find the direct link, not only to say that this happened at the same time, but to actually say that they were linked process-wise. And that's really difficult.
So what are the outstanding questions? Where are you thinking this needs to go next to try and resolve this?
I think we need to understand extinction mechanisms. What can actually lead to the demise of life on Earth. And at the moment, there is really a big confusion about processes leading to warming, for instance, and then extinction mechanisms, which is a bit different. So we need to merge the ideas about how the Earth has evolved with evidence from the field, with evidence from geochemistry, but also with what actually can cause extinctions.
Henrik Svensson.
Keeping you abreast of the world's best science. The Naked Scientists.
This is a special Norwegian edition of The Naked Scientists with me, Chris Smith. A number of animals use primitive tools. But how does this behaviour begin? And what can it tell us about how we got started doing the same thing millions of years ago? Adriana Hernandez Aguila has been to Tanzania to try to find out.
These chimpanzees that I study live in a savanna, which is very different from the typical forest habitat that you see in documentaries. They have a very harsh 6-month-long dry season, so we are trying to figure out how they can make a living there. I spent 2 years in Tanzania studying these chimpanzees, and during this time I discovered a new kind of tool use. We know that chimpanzees use tools in many different contexts, but this specific kind of tool use had not been reported before. They were using tools to dig up roots like potatoes, and this behavior is very interesting because it was one of the behaviors that people used to believe was uniquely human. It has been a lot of debate about what made us human, if it was the eating meat, the hunting, or digging for tubers, like hunter-gatherers in Africa or other parts of the world still do today.
So why had this been missed before? Why had no one seen the chimpanzees doing this?
Because tool use in chimpanzees is not present in all the populations. Different chimpanzee populations have different types of tools. So we have never studied this population before. Before my study, this place is called Ugala,
had only been short-term surveys, and I was the first one that was there long-term for 2 years. And even though the chimpanzees are not used to humans, that means we cannot follow them and we cannot observe the behavior all the time. I was also trained as an archaeologist, so the discovery was based on indirect evidence. We found the holes that they have dug up with knuckle prints from their hands, with feces, with hairs, with finger marks. And of course, we had heard chimpanzees vocalizing from those sites, and when we arrived there, the chimpanzees were gone, but the material evidence was left there.
And the tools they use, tell us about those.
The tools are very incipient. That means they are not very developed. For example, hunter-gatherers using tools also for getting tubers. The tools are very long, are heavy, are sticks, usually hardened by fire in the tip. These tools that the chimpanzees are using are expedient in the sense that they are very new. We don't think they had been using them for very long. They are very varied. Some of them wore pieces of a log that had fallen down. Others wore pieces of bark that they just scraped the soil off, we think, and then when it got easier, they dug by hand. So we are thinking that this is a behavior that has not been around for very long. So it has been, discovered not very long time ago. They haven't had time to have very complex tools to do such behavior. But the fact that they are using these tools and getting these resources makes it very interesting.
What do we know about how the chimps pass on the knowledge? Do they do it by passive observation? I watch you use that pencil to write on that bit of paper and I therefore work out how to do the same? Or is there an active teaching going on? Does a mother take a child and actively encourage it to do the same behaviour, or don't we know?
We know that from populations that are where the subjects are used to humans, so you can observe them. A lot of the tool use is by observations of the mother, usually, using the tools. Since chimpanzees live in a fusion society, that means the group never travels together all the time, but they divide in small parties, and then this party changes in composition by minutes or hours or days, so you are never with the same chimpanzees. But the only constant is the mother. Dependent offspring always travel with the mother, so they have a lot of opportunity to learn by watching how the mother uses the tools. We also know that mothers facilitate tool using. For example, when they crack nuts with stone anvils and hammers, they leave the tools for the infants to use. They also have been observed to place the nut in a specific way to make the hammering more successful. And there has been some reports of active teaching, but it has been not very common. People need to see more of this evidence to actually say that, yes, they do have active teaching.
If you can work out how the chimps evolved this fairly new behaviour from scratch, does that tell us anything about how we, or at least our earlier ancestors, evolved to use tools?
We actually think that tool use probably evolved many times in our evolutionary history, but by learning the constraints of tool use, by learning the adaptations that tool use allowed primates to have, we can learn a lot about tool use in humans and how it evolved. Actually, I was just part of a paper which compares the oldest human technology, 2.6 million years old, from Ghana, Ethiopia, with mostly chimpanzee tools. And all of the behaviors that you can infer from the archaeological record are present in chimpanzees, except for two of them, which is the distance that the tools were carried. Hominins carried tools for longer distances. The other behavior that chimpanzees do not have is that hominins competed with big carnivores of that time, saber-toothed cats, leopards, lions, and chimpanzees do not compete with these predators in Africa. So those are the only two differences that we could see. And I am actually working on a paper right now about transport, and it seems to be that if we go deep into what we know about chimpanzee transport, it's not so different from what we know about hominin transport. So it may be that we will just be left with one of the differences, which is hominins competed with carnivores. But I want to make sure that we understand that this competition is not direct, but they were having access to the same food types. They were eating meat from large animals. But we don't think the competition was direct. And there is a big debate if these hominins obtained the meat by hunting or scavenging, and we don't know that yet. Probably the very first hominins did not do much hunting.
Who would have thought that the evolutionary origins of bin raiding could go back so far? That was Adriana Hernandez Aguilar. And to round us off now, sperm, cells that biologist Terry Lascamone describes as hugely paradoxical.
They have such a simple task to reach the egg first, to achieve the fertilization, but then it's the most variable cell with respect to size in the whole animal kingdom.
What are the variations then?
You have sperm from, for instance, nematodes, these small worms you don't want inside you, which are maybe a couple of micrometers big, to Drosophila sperm, reaching almost 6 centimeters.
6 centimeters,
Yeah.
but they're flies. They're
Yeah.
tiny flies.
Yeah, that's correct. The sperm length is actually 10 times the length of the individual.
Why? And how do they use something like that?
Well, it's not fully understood actually why they are that big, but of course there will be a trade-off then. So instead of producing millions and maybe billions of sperm, they have a few, but really large ones. And for some bizarre reason, that works in these species. But that's of course an exception.
And what about the birds?
The birds, they have quite special sperm compared to human sperm people are used to. The tadpole thing, a rounded head, swimming, beating with a flagella, looking like a tadpole. In birds, the sperm are quite different. They are actually helical-shaped, the head and the midpiece. Their way of moving in the medium is actually to spin around their own axis while also beating their flagella. I like to use the phrase tadpole sperm in humans, Ferrari sperm in birds.
Are they really faster then?
They are much faster, definitely. Up to 10 times faster, yes.
The obvious question then, with that dramatic difference, is why?
Yeah, definitely. I'm working on songbirds only. To specify that, because sperm from other groups of birds are not necessarily that helical shaped.
Oh, that's intriguing.
Yeah.
Let me ask a question then. Are the birds that you're studying, are they, how do I put this, promiscuous?
Yeah, definitely.
So there's a sort of selection,
Yeah.
there's a selection going on here.
Yeah.
There's obviously, because there's a chance that the female bird is putting it about a bit and the males are also putting it about a bit, there's a strong competition going on here.
Yeah, definitely. And that's why this study system is so fascinating, because you have bird species which are socially monogamous and also genetically monogamous. And in those species we see that sperm is really variable, both within the males and also between the males. Whereas in other bird species, they are socially monogamous, so we have a mother and a father siring the offspring, but genetically highly promiscuous. So males fly around, females accept males coming. And
what fraction, if you've got that set up where you've got pairs of birds, what fraction of the offspring of that pair of birds is actually sired by the male in that pairing?
Yeah, that's really, really variable. So the extremes are fair wrens in Australia, where up to 80% of the offspring are sired by another male than the social male feeding them.
Okay, so there is massive pressure here to make sure your sperm are the ones that actually are passed on to that generation. And that's why they're going for the intense speed.
Yes, there is a relationship between speed and the level of promiscuity. The more sperm competition, the faster the sperm swim. But
so intuitively then, if the sperm are in that level of competition and speed is of the essence, then there's much more pressure to keep the size tightly focused compared with those animals and the birds that you said tend to be more monogamous. There's less pressure, so the sperm can get away with a wider variation in size and speed.
Yeah, exactly. That's what it points out to right now. Whereas there is a strong relationship between speed and this level of promiscuity, the variation in sperm size is extremely tightly linked. So, say in a monogamous species, genetically monogamous, you have a high variation in sperm size, and the more sperm competition, the lower the variation gets, until these extremes in the far end with the high, really high levels of promiscuity, with the sperm almost looking identical between males also. So we have actually published a paper stating that you can show me your sperm and I can predict your level of promiscuity.
Does the same apply to humans? No.
Well, humans are, I would say, moderately promiscuous. We have species we can compare us to. So, say chimpanzees, bonobos.
They're very promiscuous. Aren't
They are more promiscuous and they have faster sperm than us.
So it fits the model?
Yeah, it fits the model. And actually, there was a paper published some 5 years ago on this, looking at chimpanzees, humans, and gorillas. And it's in the predicted direction. So the gorillas have the slowest sperm, humans are in the middle, chimpanzees are the fastest.
So it's not just size that's important, speed,
yeah,
is of the essence.
Size. And no one has looked at this variation in sperm size in great apes yet. But there was a recent paper on insects supporting what we have found. Some people now check this out in social insects, so bees, bumblebees, and ants, and they found the same pattern. So the more sperm competition or higher level of promiscuity, the lower variation in sperm size.
A slightly delicate question to finish. Do the birds oblige when you ask them for sperm samples? Yeah. How do you get the samples?
Well, we give them a gentle massage, and this is that's an interesting question, because some people, when they ask me what I do, if I want to go the long way, I will start out telling them I'm a biologist, I'm working with birds, and so on, and finally get to that I'm working on sperm evolution. But on the other end, I could just tell them that I'm actually masturbating birds for my job. But to finish off in a more serious manner, the birds, they have these sperm storages, organs, just closely to their cloaca. That actually makes their cloaca look like a tube in the breeding season when they have the peak of sperm production. Those are actually what we're massaging to force the ejaculate out. And this is done in 5 seconds when you're experienced. You can take the blood sample as we do, take the sperm sample, measure the wing size, band the bird, and release it within a couple of minutes.
Terry Lascamone. That's it for this week. Next time, we're examining chronic fatigue syndrome. As always, the email address is chris@thenakedscientist.com. I'd like to say thank you to Nina Christensen and Ida Corneliussen, who escorted me around Oslo. I'm Chris Smith, and until next time, goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.